Hey, this is Mr. Aiden. We're going to be talking about energy levels today. Energy levels in physics honors. When we have an atomic energy level, what happens here is this. We have an electron that's on what we call the ground state. The ground state is called n equals 1. That's what they call where the electron should be. And you can see how here I have a photon of light or energy coming in. Remember, energy equals Planck's constant times frequency. And as that energy goes in, this electron absorbs energy. And when it absorbs energy, if it absorbs enough energy, it'll go up to what we call an excited state. It goes from n equals 1 up to n equals 2. Now, what happens here is this. As the electron comes back down to the ground state, it will give off the energy in the same amount of energy, and that energy comes off in the form of light. And so we can actually know how much energy is between two energy levels because we can know the light with which it gives off. You can see we have here's hydrogen gas, here's nitrogen gas, oxygen gas, mercury gas, neon gas glows like an orange color. Every single element has a distinct wavelength of light, and we'll take a look at our spectral data later on in the week for our from going from an excited state down to a ground state. So how does this work? You can see right here is we have an electron right here at the second energy state. Well, we're going to call here's the n equals 1, that's the ground state. We have n equals 2, and then we have n equals 3. So the second excited state is actually n equals 3. Now, there's 3 different transitions this electron can make to come down to the ground state. Okay, it can come all the way down from n equals 3 to n equals 1. Which means, do you see how it was at negative 1 electron volts, now it's at negative 4 electron volts. So how many electron volts did it give away? It gave away 3 electron volts of energy to go from n equals 3 all the way down to n equals 1. Now, it could also go from n equals 3 to n equals 2, which you can see what's the energy difference in that going from negative 1 to negative 2. It gives off 1 electron volt. Or it can then go from n equals 3 to n equals 2 and then back down from n equals 2 to n equals 1. Which, how much did that energy give off? It gave off 2 electron volts right there, 2 electron volts. So these electron volts that it gives off is the difference, Now, we have an equation. We actually have 2 equations. We have energy equals Planck's constant times frequency. We have the speed of light equals wavelength times frequency. And remember, together, we can actually combine these 2 equations together and say the energy is equal to Planck's constant times the speed of light divided by the wavelength, if we just want to find the wavelength. Or we can rearrange this to say the wavelength is equal to Planck's constant times the speed of light over the energy. So you can see for this first one, if I want to know the wavelength of light with which it gave off, we're going to put Planck's constant. That's 4.14 times 10 to the negative 15th, the speed of light, which is 3 times 10 to the 8th, and we're going to divide by 3 electron volts. Why are we using the 4.14? Because remember, that is dealing with electron volts. We have to use the 4.14 number for these types of problems. So we are going to do that, and I end up getting a wavelength of approximately 4 times 10 to the negative 7th meters. Try that on your calculator. Hopefully it will make sense. So we're going to do the same thing for this one. We get 4.14 e negative 15, 3e to the 8 over 1 electron volt. Okay, so we have 4.14 times 10 to the negative 15 times 3 times 10 to the 8 divided by 1, and we get about 1.2 times 10 to the negative 6 meters. And the last one here is the wavelength for this. We get 4.14 e negative 15. We have 3 times 10 to the 8th. Hopefully you can see. We divide by 2 electron volts. So we have 4.14 times 10 to the negative 15 times 3 times 10 to the 8th divided by 2. And I get 6.21 times 10 to the negative 7th meters. Now, if I convert these into nanometers, remember 1 nanometer equals 10 to the negative 9th meters. So if I do that with this guy, 4 times 10 to the negative 7th divided by 10 to the negative 9, I end up getting 400 nanometers. This guy, we have 1.2 times 10 to the negative 6. I divide by 10 to the negative 9th, and I get 1200 nanometers. And this one is about 621. Let me put an equal sign there. 621 nanometers. Okay, 621 nanometers. Now, think about that logically. This n equals 3, and I'm going to do different colors so that we don't get mixed up here. Let's say I have these 3 electron volts, okay, which means we go from here all the way down here. It's going to give off a wavelength of light of 400 nanometers. From here to here, well, let's see this 2 electron volts. From here to here, that's going to give off 621 nanometers, right? So that's going to give off 621 nanometers. And this guy right here is going to give off 1200 nanometers. Now, think about this in terms of the electromagnetic spectrum. Now, do you see how the one with the smallest difference in energy is the largest wavelength, because that's inversely proportional. The one with the largest difference is the smallest wavelength, the most energy. Okay? And think about our electromagnetic spectrum. Take a look. 400 nanometers is like a violet color, a blue color. So 400 nanometers is going to be kind of that violet blue, high energy, isn't it? 621 nanometers, you can see 621 is going to be kind of an orangish red color coming off. 1200 nanometers, well, 1200 nanometers is all the way over here in the infrared. We wouldn't even see this light. It would be infrared. We wouldn't even see it. It would be out of our spectrum. Okay. Let me give you here. You can see how we're looking at our energy differences. If we go from n equals 3 to n equals 2, we're going to be going from the difference. Remember, we subtract these numbers to find the difference. The energy level would be 7.56 electron volts. We're looking for the difference. From n equals 2 to n equals 1, we're going 54.4 minus 13.6, and that's a difference of 40.8 electron volts. And what about if we do this full transition from 54.4 from the 6.04, that from n equals 3 all the way down to n equals 1 is going to give you about 48.36 electron volts. And what can you do? You can do energy equals hc over the wavelength to find the wavelength of light that is given off by each spectrum. Now you can see how the one with the largest energy is going to have the shortest wavelength, right? Which means that's going to probably be up near the UV spectrum, okay? Near the UV spectrum, which means the UV spectrum, now this is probably going to be the visible spectrum in the middle, and this is probably going to be the infrared right here. So we can see we can know by the energies and the wavelengths of what happens. Let me give you one last type problem. Here it says the figure above, we have a hypothetical atom. The wavelength emitted undergoes transition B as 400 nanometers, right? 400 times 10 to the negative 9. So the wavelength is 400 nanometers, or 400 times 10 to the negative 9 meters. Okay, so I'm going to find the energy of this, and I'm going to do hc over the wavelength. So we have 4.14 e negative 15. We have 3 times 10 to the 8th. We have 400 e negative 9. So 4.14 e negative 15 times 3 times 10 to the 8th divided by 400 e negative 9 gives me a 3.105 electron volts. So I know this one is 3.105 electron volts, this transition. Transition C is a wavelength of 700 nanometers, or 700 times 10 to the negative 9. And so I'm going to find the energy, hc over wavelength, the exact same way. 4.14 times 10 to the negative 15 times 3 times 10 to the 8 divided by your 700 times 10 to the negative 9, and I get an energy of 1.77 electron volts. So here I have 1.77 electron volts. Can you know what this full energy is right here? Sure, you just add it up, 3.105 plus 1.77, and I get the energy is equal to 4.875 electron volts of energy. Can you find the wavelength of this? Sure. All we have to do is hc over the energy, and that gives you the wavelength of that transition A. So that was energy levels. Energy levels, it's sometimes hard. Students think right off the bat, but as you can see, it's the same equation over and over and over and over again. See you guys. Have a good day.